Okay, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Thank you so much for joining us in our first talk for the year under the Photonics lecture series. With me today, I am Dr. Nadia. I am the Vice Chair of IEEE Photonics Society Malaysia. I am also from Universiti Putra Malaysia. With us today, we have Miss Nurul Farah Adila, which is from UTM. So before I let her take over the stage, let me introduce her a bit. Where is it? Okay, give me a minute. So Miss Nurul Farah Adila Zaidi received her Bachelor of Engineering in Electronic System Engineering from UTM Malaysia in the year 2019 and her Masters of Engineering in Management of Technology from Yamaguchi University from Japan in 2022. She is currently pursuing her PhD, soon to graduate, focusing on the development of AI-powered optical fiber sensors for advanced sensing applications. And with that, I would like to invite Ms. Nurul Farah to present her talk today. The stage is yours.
Assalamualaikum and good evening, everyone. Thank you to the IEE Photonics Society for giving this opportunity for me to talk, which is this is a part of my PhD project, and I think this platform is very good for me to have a connection with all of you guys and sharing some parts of my PhD journal. So, so can we start directly right now? Can everyone see my screen?
Yes.
Okay. So today I will present part of my PhD research, which is AI-powered optical fiber sensor, advancing MMI for wide range RI detection. So I am Nurul Farah Adila binti Zaidi, and you can call me Farah. I'm from Lightwave Communication Research Group, Faculty of Electrical Engineering, Universiti Teknologi Malaysia. So this is just a reflection of part of my journey when I'm doing PhD. So for the first and half year of my PhD, I based in UTM Kuala Lumpur for me to doing the simulation on the fiber and some of the experiment there in UTM Kuala Lumpur. And the rest is I'm doing my work in UTM JB base. So on my second year, I went to Lakehead University for a research attachment to analyze the characteristic of the oil at that university. And this is some of other conference that I joined and poster presentation that I joined and some of the AI training to improve my my skills on AI base. So that is just introduction of me. So today I will present about this is the outline. What I want to present today is the introduction, and then of the optical fiber sensor experimental setup and how AI integrate in this experimental setup and why we use AI for analyzing our data. And the fourth, I will show some result and key finding, and the last is the conclusion. So what is AI-powered optical fiber sensor advancing MMI for wide range RI detection? So I hope that maybe some of us are not in the same field, but in the photonic, maybe someone will ask what is MMI, what is RI, why we need wide range of RI, and AI, I think obviously everyone know what is AI actually is. So basically, what we do is we develop a sensor that can detect a wide range of RI for low refractive index and also high refractive index, and we analyze the data by integrating artificial intelligence. So this is the introduction. People might say, what is refractive index? Why do we need wide range RI detection? What is MMI fiber sensor? Why AI? How does it help improve sensor RI detection accuracy? And what the application? So this is very important, and I will go through one by one. So what is refractive index? So basically, refractive index is a measure of how much light slows down and bends when passing through a material. So you can see the figure on the left side, where we have a light entering from the air medium, which is a 1 RIU. RIU is the standard unit for refractive index, and entering to water medium, which have 1.33 RIU, which is a higher refractive index value compared to air. So here we can see the light reflect away from the normal line. But at the right side, you can see the light entering the air, but entering to the glass part. So we can see the light reflect near to the normal line. And it different with the other one at the bottom, which is the light inside of the glass, which is the higher refractive index, and go through to pass the air, but the light will reflect inside. So I will, this is part of the phenomenon like total internal reflection and also fluorescent reflection. But I will go through in this section on based on my experiment later on. So why wide range RI is important? For example, we have a fiber sensor. As I mentioned, is refractive index is a material, whatever material they have their own refractive index. So for the fiber sensor, the one that I use is a silica base, which the RI of the fiber is 1.4440 RIU. So in order we want to detect water. So water, they have their own refractive index, which is 1.33. So here we can see that water have lower lower RI when it's surround to the fiber sensor, meaning that this application is for low refractive index application. And compared to oil, which have higher refractive index, meaning that this sensor sense something surrounding medium that have high refractive index. So this is very important. For example, we want to sense the water quality assessment, and then we want to sense oil degradation. That's why we need this kind of sensor that can sense wide range RI. Wide range RI. Okay, so we back to the basics of the fiber optic. So fiber optic, they have in various field of technology, such as sensing application, lighting system, communication network, and data storage. However, I want to focus on the sensing application only for today. So what is the advantages of the optical fiber sensor? So we know that it have high sensitivity. That's why it's good. Fiber optic is good to use on a sensing application. It rapid response, compact size, where we can bring this fiber optic for real implementation, multiplexing capabilities, chemical inertness, immunity to electromagnetic. And then we go to the sensing parameters. So usually fiber optic have been used for refractive index detection, temperature, bending, chemical inertness, moisture, and pressure. So basically, fiber optic can be used in many way, like sense the temperature, for example, for bending, sensing. Okay, so in which application that fiber optic is implement? So usually optical fiber sensor have been implemented in many applications like biomedicine, structural health monitoring that implement bending, and chemical and biological sensing where moisture and pressure is involved, and also oil and gas exploration, where we can find that currently they use fiber optic to detect the acoustic gas leaking at the platform. So this is the basic fiber optic cable structure. So as we know, like our mobile phone have outer cable jacket, however we cannot see the insides of the fiber. So basically this is the basic fiber optic cable structure that consists of polymer coating, cladding, and the core part. So usually the core part is the sensing part, which is very important for sensing application. Okay, so this is a few essential fiber types in optical sensing. However, there is more other fiber types in optical sensing, but I just want to show on why in this study I use MMI no-core fiber sensor. So this is the comparisons of the single mode fiber, multi-mode fiber, and no-core fiber. So based on the introduction before, I asked what is the multimode interference. So here we'll show the difference of multimode interference. So for the single mode fiber, we can see the core part, the diameter of the core part is narrower, meaning that the light is straightly and guided inside of the core. And this single mode fiber have a cladding, a thick cladding. So for the sensing, usually people will remove this part of cladding. Same goes to the multimode fiber also. They will remove the cladding part and use the core as a sensor. So maybe if we doing something on the cladding, meaning that we etching or tapering or involve acid to remove the cladding, maybe they might affect the durability of the fiber itself. So for the multi-mode fiber, you can see they have a large diameter core which have a few modes inside, which is higher order mode and lower order mode. So usually for the sensing part, the higher order mode will leak out to the surrounding, where it will sense the surrounding medium. And so this is the reason why I choose no-core fiber. No-core fiber, from the term itself, it highlight, which is the fiber, there is no core of the fiber, meaning that the cladding act directly as a sensor. So the cladding part is the sensing part, and they can sense the surrounding medium directly. Okay, for the sensor design MMI structure, so we choose a no-core fiber in our experiment because we can see it is very simple design, easy to fabricate, because the size of the no-core fiber itself, the sensing part, is the same size of the cladding of the SMF. So we can see from here, the core fiber of the SMF is 10 micrometer, but for cladding is 1 to 5. So the cladding part is have the same diameter with the no-core fiber. So we want to minimize the loss, and we utilize this single mode fiber is just for light propagation, since the core is very narrow. So we use single mode fiber on both sides for the light propagation to get the output result. And additionally, the Ri of the no-core fiber, since it is made from pure silica, so the reference of the Ri is 1.444, and for since this is silica design, it is resistant to temperature. Okay, so this is the fiber principle, where when the fiber of 1.444 detects something surrounding medium that have low refractive index, so guided mode interference will be the theory. And for at the right side, where the surrounding medium have the high refractive index, some portion of the light will be extend into the cladding. So this experience the Fresnel reflection. So by comparison on between this guided mode interference and also leaky mode interference, guided mode interference is basically is ideal for signal transmission, meaning that we don't want any information will leak out to the surrounding something else. So it will guide it inside of the fiber. But for leaky mode interference, is ideal for sensing application, where some part extend into the cladding, so we can send something outside the surrounding medium. Okay, this is the sensor preparation on how I connect the single mode fiber, no-core fiber, and also single mode fiber. So basically, we need to remove the polymer coating of the fiber, and then we combine it using we cut it using cleaver and splicer, and I believe this is the same method as someone's research regarding fiber also. So for the splicing method, we ensure that the loss is very, very low, because we don't want any power become lower. We don't want any we don't want the fiber have a lower power when we send something outside of the fiber. So we need to do this preparation carefully. Okay, so this is the experimental setup, which involved the broadband light source, and then the sensor, and also we analyze using the optical optical spectrum analyzer. So this is the experimental. So in this experiment, I use a low refractive index, 10 sample of low refractive index, which is the range is 1.30 until 1.39, and for high refractive index is 1.46 and until 1.55. So with the step size of 0.01, meaning that I test the refractive index on the sensor for 10 cycle, and for high RI also for 10 cycle. So alcohol and dry tissue have been used for cleaning purpose whenever I want to change the RI for the next RI. So we need to clean the sensors first and then record using the optical spectra analyzer. Okay, so this is the preliminary result of the transmission spectrum analysis. So the blue color, you can see it's referred to the spectral output profile of the light source itself, meaning that the light source is directly to the optical sensor analyzer without the sensors itself. So we can see that the power is very high here, and for low refractive index, I drop only one RI, for example, is 1.35. So a distinct attenuation and transmission band are observed here. We can see any other peak and also dip on this transmission when we detect the low refractive index. However, for high refractive index, the bands become less defined due to power leakage resembling the transmission profile of the PLS, meaning that for the high refractive index, it's resembling the transmission profile, but they have a lower power. This is because the power leakage during this light propagation. Okay, so this is the whole result when I drop 10 cycle of refractive index, 10 bottle of refractive index, and also 10 drop of high refractive index to the sensor. So we can see that the intensity changes and wavelength shift in the low refractive region occur. However, for the high refractive index, only the intensity changes for the high refractive index. We can see the power attenuation only, but for the low refractive index, we can see the power attenuate, but somehow they shift to the right, to the red shift. Okay, so this is the result. So here we can observe that there's a changes in wavelength shift and intensity for both LRI and high RI environment. So for peak power, we can see for the low refractive index, there is a significant change on the power. So we can refer from here, there is a significant change on the power. And also for high refractive index, 1.46 until 1.45, also have a significant changes, but the power become more strength when the high RI increase. This is due to the phenomenon of the leaky mode fiber, where when the mode is overlap between the guided light and also the surrounding medium, so it yeah it the power coupling become more strength on this. However, for this structure, we can conclude that this no-core fiber sensor is good to sense both low refractive index and also high refractive index. However, when we can see from the graph itself, the power is around -40 until -30, which is almost the same for the low refractive index. So how we can differentiate this? Let's say we have a lot of spectrum, a lot of refractive index come into the sensor. How we can differentiate on this, because there's overlapping occur on this sensing spectrum. So maybe it might have issues on this, where we can just analyze using traditional method, but it's not that accurate as what we want the system to be sensed. Okay, so the main problem is the ambiguity in sensor data. So we can see from here is the overlapping power response, so causes interpretive challenges across wide RI range. So this is very important on detecting of wide RI range, because we don't know how wide is the RI is. So we need a machine. We need a machine to learn on this data. So the second one is the data ambiguity. So it is limits traditional method. It might reducing the RI detection accuracy due to complex spectra. So let's say we have a complex spectra and a lot of data here, and how we can analyze this and how we can differentiate whether it is low refractive index or high refractive index value. So that's why we need AI. Okay, so this is the key concept for today, where we use the experimental data from the experiment, and then we train the model using MATLAB R2024B toolbox, which there we have a few simple machine learning model that we can use there, and then we train the model and we will get the result. For example, like the regression on how lower refractive index and high refractive index is respond to the predicted value. And the second one is the record number, where we can see how this low refractive index and high refractive index, this model can train over time. So this is very important for real application. Okay, so I just want to give the overview of AI. So what artificial intelligence is? So basically, artificial intelligence is like a home where a machine and deep learning was inside. Is a subset of the artificial intelligence. So as example, artificial intelligence is we want a smart system, for example. So there's problem and what decision that we need to do for artificial intelligence. So for the analogical term, we can say that, okay, we want a cake, the whole cake, and then how we want to make a cake. So that's why we need this machine learning to based on the analogical, where we need the recipe to make a whole cake. So same like machine learning, where we need to train a lot of data to get a smart system. So it's just the same for deep learning, where we need to train many layers of the data instead of a sample of data like machine learning. And for based on the analogical, we want a fancy layer cake, meaning that we need another recipe, we need another flavor for the cake, for the cake layering, for example, to make a layering cake, fancy layering cake, instead of the whole cake, the usual whole cake. So basically, that is artificial intelligence. So this is another example of artificial intelligence in order for us to understand what is AI actually. So here we can see a kid where her mom teach her about to play a Lego. They have a shape and they have a color. So when once mom give the input to the baby, and then the kids can understand, and somehow when she or he grows, she can understand what is the shape and what is the color of the Lego itself. So basically, that is the overview of the artificial intelligence. So next we go to the ML process, like a recipe of the cake, what we need for the process in order for us to have a good system, for example. So we need the data collection, model selection, a good model selection, data splitting, where we need to train, if we have 100% of data, and then 80% is for training and 20% is for validation. So this is very important. And then give the model to train and to evaluate the results of the data. So basically, this is the process machine learning. So in machine learning model also, they have a few type of machine learning, but here I just compare between the decision trees, support vector machine, and also neural network. Before that, we can optimize the ML method, which we can use classification or regression. So basically, classification is we use the data and then we classify the data into two, for example. So in my case, if we classify the data like low refractive index and high refractive index, but this is a continuous data where we need the answer is in numbering form, which is like what is the RI on this spectrum, for example. So we do the comparison using the MATLAB tools, comparison on the classification and regression, where we can find that neural network for regression accuracy have the higher accuracy. So we choose to use neural network in our study in order to have the accurate RI prediction using the model. Okay, so what neural network actually? So basically, neural network is like a neuron inside of your brain. So when you see a cat, like the kids see a cat, meaning that the kids gather the information, and then the brain of the kids, they analyze the data, and then they know this is a cat, but it is not a dog. It's like that. So in our case is we train the data that we got from the experimenter, including low refractive index and high refractive index data, and we insert to the training model, which is we use bilayer neural network. Bilayer neural network is meaning that the layer have two layer, and the number of neuron we can adjust from to make the accuracy more accurate. And the result is the RI prediction. Okay, so this is the spectral analysis with neural network comparison. So here you can see a few models of neural network. So I use this toolbox in MATLAB. I, I can, for the narrow neural network, they only have single layer but 10 neuron. For medium, they have 100 neuron in one single layer also, and wide, they have 1000 neuron, but it's still in single layer. However, when I increase the number of layering, the regression become increased, and we can have the high accuracy on this, which is 99.7% accuracy on detecting the RI detection. However, this model is only fit for our data set that we have. Okay, so for the result, how I can prove that this bilayer neural network model is good for RI prediction. So you can see from the graph, this is a comparison of predicted versus actual refractive index value for binary neural network regression model. So it shows that high accuracy, the BNN model closely match predicted and actual, meaning that only sums of the part is far away from the line. And this work across all RI. The model performed well for both low refractive index, meaning that the value is not mixed match too, but they separate between the low refractive index and high refractive index. And this reliability of the BNM model can enhance the performance of MMI. Instead, we depends on the way of the traditional method that we study the sensing of the sensitivity of the sensor based on the wavelength shift and power attenuation for both low RI and HRI, high RI. Okay, next is the response plot, which is this is the predicted RI values against record number. So this is the response where low RI and high RI to predict accurately over the time. This is important if you want to implement to the real application. So here we can see the consistency where the plot show the model ability to predict accurately over time following the actual data without significant error. Even here we can see the differentiation of the low refractive index and high refractive index. So it shows that the performance have a close alignment of orange and blue dots indicate that the model reliability across the data sets. So for the practical importance in real-time application, accurate and continuous prediction are essential. That's why this model is can prove that this model is good for the future usage. Okay, next is the residual plot of RI. So you can see here is a random scatter that the dots are randomly scattered around the middle line, meaning the model is making prediction without any big errors or pattern. So you can see the scatter with no pattern, which is good because the model is learning well and not making mistake in one area more than another. So this also have shown reliable on both low refractive index and high refractive index, where the plot doesn't mix and match in this range. Okay, lastly is the Shapley value, where Shapley value showing how each wavelength feature impact the BNN model's prediction. So as I already shown from the data that we have, like wavelength over power as an input, and then we train the data and the output is the RI prediction. but we want to know how the model works on this and which feature that impact this model. So I extract only one RI. For example, for low RI is 1.3 and for high RI is 1.55. So from here we can see the wavelength of 1559.74 give a good impact features to the BNN model, while for high refractive index the wavelength is 1529.32, give the wavelength feature impact to the BNN model. Even though we can see here for low refractive index, we have the same wavelength, and also for high refractive index 1559.74, meaning that this wavelength have give a good uh, feature impact into both low refractive index and also high refractive index towards to the model. Okay, so this is the comparisons of AI-based optical fiber sensor for RI sensing. So at the bottom is my current work, which is I use bi-layer neural network, and the data I was extract from the experimental, and the configuration of the fiber itself or the sensor design is very simple, where we just need to connect the SMF, Noco fiber and SMF, compared to other that involve coating, something like that, which will affect the reliability of the fiber when it connect with the single mode fiber, for example. And then for the range, we can see most of the range detection is focusing on the low RI, and then they're doing the AI part here, mostly based on the simulation and some part of the experimental. So we can compare that with our work that can sense both low refractive index and high refractive index, and also we get a high accuracy on using bilayer neural network model machine learning. So for the temperature cross sensitivity, since we use Noco fiber, we can negligible the temperature cross sensitivity, since it made of a pure silica and can stand in a high temperature. For the model approach, I already showed the comparison on why I choose regression on this study, because one of the reason is the data set that we have is in a continuous data, so regression is the best for the model approach. And I think that's all from me. So for the conclusion, we have a high accuracy MMI fiber sensor, where we integrate the AI to enhance the accuracy and for wide range RI. And the sensor that we use itself is very simple, where we just need the process of cleaving and splicing the fiber, and it made of silica, as already mentioned. It is temperature resistant. So effective for complex sensing. For number 3, this model, BNM model, can resolve the overlapping spectral signal that we observe when we do the experimental, and then we know that there is overlapping between the power of low refractive index and also high refractive index. And we need this model to resolve and study the trend of the spectrum, so that we can get the correct RI prediction. And then for the last one is the practical application. The approach provides a reliable, real-time sensing solution for diverse environmental and industrial application. Okay, so this is a sum of my list of publication along this PhD journey, and hopefully that some of my paper also will be accepted soon. And I think that all from me. Feel free to connect with me for more discussion on collaboration or something else. Thank you.
Oh, well done for the very interesting talk. I think this is a different flavor from what we have had so far in the previous years. So I'm very grateful for that. So we have a question from the audience. Someone raised their hand just now.
Okay, sure.
Um, I'm not sure who it was. Kata silap tekan. Does anyone have any questions? Okay, Dr. Akmar, go ahead. Dr. Akmar, you may ask your question.
Hello.
Yes. We can
Okay,
hear
sorry,
you.
sorry.
Yeah.
All right. Thank you, Nurul Farah, for your great presentation. Okay, I just have like one question because just now, what did you presented? I mean, seems that your model has successfully showing accuracy, isn't it? I mean,
Yes.
good, very good accuracy. You have achieved that. Okay. Did you come across any outliers from your data or from your values throughout your research? So if outliers data, because when we did some experiment, normally we get these outliers data. So if yes, how did you manage them in training using your machine learning model that you have chose?
Oh,
Right,
so
thank you.
thank you for the question. So basically, we didn't import any other data that from the outside because currently we train only the data set that we have from the experimental work, but we train the whole spectrum without any bias. I mean, like whatever data that we obtain from the experiment, that is the data that we train, and then we playing with some of the model and hyper parameter on insides of the model. That's all.
All right, thank you so much. Yeah, this is quite new for me also, so it's a good insight. Thanks a lot.
Thank you so much.
Thank you, Dr. Akmal. We have another question from the audience. Dr. Wei Ling Oi, thanks for your sharing. There is some questions from me. How many sets of data did you use to train your model? Also, where do you get the data set for this model training?
Okay, so I'll try to answer your question. So basically, of course, for this presentation, I didn't touch into the how the model works inside, but I can share. Uh, the first one is how many sets of data did you use to train the model? So basically, we have a few RR, right? So we can observe from the spectrum that I show, we have a 20 spectrum. However, we collect each of the data sets. One refractive index, we have around 334 data point, meaning that if we have a 10 cycle of spectrum, we need to time by 10, which is 3,340 for one spectrum only. However, we have a 20 refractive index, meaning that we need to times by 20, which is around 32, around 60,000 something. So that's how we get the data set to train the model. So second question is, where do you get the data set for this model training? So the data set, I do the experimental by myself, and then the whole spectrum that we obtain from the experiment, we give to the machine learning to learn the pattern of the spectrum itself. I hope that I answer your question, Dr. Wei Ling Oi.
Thank you for the question. Another question that we have from the audience is from Dr. Muhammad Yusuf Muhammad Noor. Can the same model AI be applied to other types of sensors, for example, FPG sensor?
Mm, okay, so for this question, of course, whatever sensor or whatever data that we have, we can train by the model. So for my model is actually is a supervised model where we have a labeling, where we have the label of the data, meaning that we have a spectrum and we know that the data is for this kind of RI, meaning that for one spectrum, okay, this is 1.36. So we can train the data because we already label and make the neural network learn until they get the result, the correct result. So I think whatever sensor we can, and since we have the input and also the output, we can train the model to get whatever we want.
Thank you for the question and for the answer. Any other questions from the audience? Okay, hi, Miss Hanim, Dr. Hamim Akmal, you may ask your question. Was that a typo? I mean, did you raise your hand? Okay, so the person disappeared. I have a question. So if a student wants to pursue something similar to you, meaning to say they want to connect these two fields together, photonics as well as AI, how would you suggest the student approach this? Should they study the AI more? Like, how did you do it? Like, what's your tip for success?
Okay, so I have not much tips, but it's a good things where we can integrate between the sensor and also artificial intelligence. And I suggest that like for me, I'm not go too deep into the machine learning, but only some part of the machine learning. But I try to train the model and get the output and try to get the output whatever I want. So meaning that in the future maybe I can improve to make the sensor can detect many any other parameters like temperature or bending. So I suggest that to master the sensing part first, because it's involved the principle also the theory itself, so then we can implement it to the artificial intelligence. So once you have that core, and then you can implement it to the artificial intelligence, since we also know the output of what we want at the end.
Okay. Good tips. I have another question. So, how long did it take you to complete your data set? Because you mentioned it was around 60,000, right? 60,000 data set. So, how long did that take you? And how did you keep your motivations high in collecting results?
Yeah, it's a hard question because I think the sensor design also what we can say, because I use the simple sensor design, so maybe it's easy for me. And then it took like maybe around 1 year to have a difference to collect to have a different designs of the sensor, because we need to know the we need to consider many things on the sensor itself. So yeah, so it
So, it
depends.
took you 1 year to decide on the sensor and then another year to collect data? Is that what you're saying?
Sorry.
It took you 1 year to decide on the sensor itself,
Oh
or
no, no,
1 year to
I mean
collect?
like yeah, to collect the data.
Oh,
Uh,
okay.
because this is not the only sensor designs that I did. So a few more design, and when we involved with the refractive index, maybe when we want to change to another refractive index, maybe the refractive index will be redundant, meaning that if you put 1.30 and then you clean it up and then you put another refractive index, maybe the result is not that good as what until I achieve this result.
Do we have any other questions from the audience? Oh, Dr. Akmal has another question. Go ahead.
Sorry. No, just now you mentioned when you wash your connected no core and SMF, right? Okay, you need to wash every time you want to change your RI sample. So, have you encounter any break the connection? Is it very hard to do so? Because when dealing with fiber optic, and then of course the silica one is very
Yeah.
hard, difficult. Yeah, it's quite challenging. So, can you share your experience on that? Thank you.
Yeah, yes, of course. When we're dealing with a micro, a small fiber, of course they will break and something. So when we need to remove with the alcohol for the cleaning process, of course, sometimes the fiber is breaking. But I think for no-core fiber, they have because we use that no-core fiber directly as a sensor, meaning that we don't have to etching or remove the cladding part. So I think this no-core fiber, this sensor design is more fragile compared to the other sensor. I guess that's why I choose no-core fiber in my work.
All right. Thank you. Thank you. All the best for your PhD.
Thank you so much.
All right. Okay.
I do have a question.
Yes, go ahead, Miss Nurul Nadia.
When you are taking your data, right, is there any problem that you face, like there's high noise in your spectrum that makes it hard to read the whole data, or you said that your data might you might encounter a few issues in terms of overlapping spectrum, which is why you pursue in doing the AI, right? So in terms of data processing, like how did you do it until you get the accuracy? Because as far as I know, you need to do all the normalization, the conversion and so on until you get the performance matrices in order to get the most accurate one lah for your ML model. So can you share a bit about that one, that part?
Yes, of course, because we have limitation in our laboratory where the light source itself, we have not that wide range of light source. So for example, especially when I'm dealing with the high refractive index where the data that we get is, we cannot read the data because the power is too low because most of the light is leaked out. So basically, we try to do many times in order to get this data and to choose this range also, because it might affect the result that we get, because based on the light source itself we have a narrow range, meaning that the result we cannot see like the overall result when we drop the oil onto the sensor. So it's like that. Is it I answer your question?
Yeah, but again, when you telling us about the slide where you told us that you got like when you're using bilayer neural network, you got like 0.99 and
Mm-hmm.
then there's an accuracy of 99.27 using this BNN, right? So how do you assess it? How do
Okay.
you get this? There might be some performance matrices that you did, right,
Mm-hmm.
for
Yeah.
this AI model.
Okay, so basically I use a tool inside of the MATLAB, where MATLAB already have already have some tools. For example, like for the simple machine learning, like decision tree, support vector machine, and also neural network. So basically, behind on that how it works, I already read inside of the network. For the neural network, they have like a few hyperparameter that we need to tune. However, for this study, I just show when I use the general setting of the toolbox itself. So for the hyperparameter, for example, like the iteration, meaning that the model iterate the result. For example, like if the data is not accurate yet, the neural network still work until it get the accurate data. So that is how the machine work inside of the toolbox. Yeah. But I'm not working it manually, that's why, but I can know insights of the toolbox, what we can tune actually, and but I just use the general setting. We can get the high accuracy on this data. So if we want to get more accurate, we can play around with the hyperparameter inside of the toolbox.
Understood. So basically, it's automated inside the MATLAB toolbox, lah.
Yeah, for
All
this case,
the
I use the
results that you
general.
got.
Yep.
Faham. Okay. Thank you.
Okay, one last question. Kesian Miss Farah.
Okay.
Any more questions? Can we get what do you call this? Photo with everyone? Can everyone turn on their cameras and so that we can take a photo? May I know where the recording will be shared? Yes, we will be sharing it on YouTube, our YouTube, and then we will be publishing the link on all our social media. Is that okay? Okay, so I hope everyone can turn on their cameras and so that we can take a photo just for the memory and for social media purposes. Tile, change layout. Okay. Okay, say photonics. 1, 2, 3. Thank you, everyone. I'll see you in the next photonic lecture series. Bye-bye.
Thank you so much, Doctor, for inviting.
Oh, thank you so much for your talk. It was very good. Very glad to have you.